Hello student, myself Nimesh Prabhakar. Welcome to Antenna and Propagation lecture series. In my previous lecture, we discussed about the radiation pattern. Now, in this lecture, we discuss about the radian and steradian. Then we discuss about the beam solid angle. Then next we discuss about the radiation intensity. Then next we discuss about the directive gain and directivity. Then next we discuss about the radiation efficiency. Then next power gain. Then relation between the gain and directivity. So in this lecture we will discuss about this topic. So now we start with the radian and steradian. So what is radian? And what is the importance of radian? Why we study about the radian and steradian? First we discuss here. So to understand the radiation pattern, these two parameters, or we can say these two definition is very important. First one is the radian and steradian. So we study the radian and steradian. So first we understand what is the radian. So the one radian is defined as a plane angle with its vertex at the center of circle with radius r that is sustained by an arc whose length is also r. So this is the definition of the radian. You can see this figure is indicate the radian. So one radian is defined as a plane angle with its vertex. We can see this is the center vertex at the center of the circle with radius r that is sustained by the whose length is also r. So here this blue portion in the circle is indicate the one radian. It is represented as unit radian. The total circumference C of the circle with radius is given by, we know that the circumference of the total circle is C is equals to 2 pi r, and thus we can say thus over a complete circle there are the 2 pi radian. Now we discuss about the steradian. So this is the figure to understand the steradian. So one steradian is defined as a solid angle with its vertex at the center of the sphere, the radius r that is sustained by a spherical surface r equal to the that of the square with each side equal to r. So this is the definition of the steradian. So now we understand what is the difference between the radian and steradian. So radian is indicate or the measured angle in 2 dimensions, and the steradian is measured angle in a 3 dimensions. So this is the basic difference between the radian and steradian. The angle in the steradian is expressed as SR. The area of complete sphere is given by, we know that the area of a complete sphere is nothing but the 4 pi r square. Thus, over complete sphere, the solid angle is sustained by 4 pi steradian. Now, we can write the steradian equation as a, or we can say 1 steradian is equals to solid angle of sphere upon 4 pi. Or we can also define steradian in terms of the radian as a 1 steradian is equals to 1 radian square. We know that r square. So that's why we write here the 1 radian square. And we know that the 1 radian is equals to nothing but the 180 upon pi. So 180 upon pi square. So when we solve this equation, so we get this answer as 1 steradian is equals to 3282.81 square degree. So this is the relation between the steradian and degree, or we can say as the radian. The area, or we can say the area ds of the surface of sphere with the radius r is given as ds is equals to r square sine theta d theta d phi meter square. So this is the area indicated by the ds. Hence, the element of solid angle of sphere is given by dO is equals to ds upon r square. So this is the equation for the element of the solid angle. It's nothing but a ds upon r square. We know the value of the ds is equals to r square sine theta d phi. So we can write as a ds upon r square. So nothing but a sine theta d phi steradian. So this is the steradian. And now we understand the beam solid angle. So this is the most important to understand the radiation pattern, because first we understand the beam solid angle, then we understand the radiation pattern clearly. So it defined as the integral of normalized power pattern over a sphere. It is given by ohm A, or we can say as the beam solid angle is equals to phi is equals to 0 to 2 pi, theta is equals to 0 to pi integration PD and theta phi sin theta d phi. Here this PDN is indicate the normalized power density, and the double integration is indicate the beam solid angle. Double integration is indicate to cover the whole area in the terms of the theta angle and the phi angle. So this is the equation is for the beam solid angle. But we know that the d ohm is nothing but the sin theta d phi. So we can write the beam solid angle as ohm A is equals to phi is equals to 0 to 2 pi, theta is equals to 0 to pi integration, and PD and sin theta phi is into d ohm in terms of steradian. Or we can also write the equation of the beam solid angle in terms of the theta sp and phi sp. So here the question comes in our mind, what is a theta sp and what is the phi sp? So theta sp is indicate the half power beam width in the theta direction, and phi sp is indicate the half power beam width in the phi angle. What is the half power beam width? We will understand later in this lecture. So this is the beam solid angle, and now we understand the next one point is the radiation intensity. The radiation intensity is defined as power per unit solid angle. So the definition for the radiation intensity is related with the power. So that power is radiated per unit solid angle. That means the power radiation in the 60 degree, 90 degree, that is defined as the radiation intensity. It is expressed in watt per steradian. So unit of the radiation intensity is the watt per steradian. The radiation intensity of antenna is defined as U theta phi is equals to R square PD theta phi. So this is the equation for the radiation intensity. Total power radiated can be expressed in terms of the radiation intensity as P radiate is equals to phi, so integration theta phi is equals to 0 to 2 pi, theta is equals to 0 to pi, PD theta pi R square sin theta d theta. So this is a power radiation equation. But we know that the d ohm is nothing but a sin theta d phi. So we can write the power radiation equation in terms of the beam solid angle as this. So this is nothing but the relation between the power radiation and radiation intensity. The power radiate is defined as a P radiate is equals to integration phi is equals to 0 to 2 pi, integration theta is equals to 0 to pi, and U theta phi d ohm. So this is the relation between the power radiate and the radiation intensity. The average power intensity is expressed as U average is equals to P radiate upon 4 pi. Now we discuss about the next one term is the directive gain, or in other terms we can also write as a directivity. So what is the directivity? Directive gain is defined as the ratio of power density to the average power radiated. We know that what is the power density PD and the average power radiation, or we can also write the P average. So this is the, we can write as the GD theta phi is equals to PD theta phi. This is nothing but the power density, and the P average is nothing but the power average. So ratio of the power density upon average power is nothing but the directive gain. But we know that the relation between the power average power and radiated power is nothing but the P average is equals to power radiate upon 4 pi r square. So now we substitute this value in this equation number 1. So we get GD theta phi is equals to PD theta phi r square upon P average upon 4 pi r square. So hence directive gain can be written as GD theta phi U theta phi upon U average. So this is nothing but the radiation intensity 4 pi U theta phi upon power radiate. So this is the radiation intensity and gain. Now directivity. The ratio of maximum power density to average power radiation is called maximum directive gain, or we can say that the directivity of the antenna. So it is denoted as GD maximum, or we can write as a D. D is indicated directivity. So D is equals to, or we can say GD maximum or a directive gain is equals to PD maximum upon P radiate upon 4 pi r square. This is the average power, and we know that the average power relation between the power radiation. The directivity can alternatively define as D is equals to GD maximum U maximum upon U average. So this is the relation between the directivity and radiation intensity. And we know that the value of the U average, or the equation of the U average, so we can write as a U maximum upon 4 pi radius, P radiate upon 4 pi. This P radiate is indicate the radiation power. Directivity of antenna is dimensionless quantity. So there is no unit for the directivity. It is also defined as D is equals to 4 pi upon ohm A. So ohm A is nothing but the beam area, of we can say the beam solid angle. So this is the relation between the directivity and beam solid angle. So here we see this is the 3 equation for the directivity. Now next one we discuss about the radiation efficiency. The efficiency of the radiation. So if the practical antenna has ohmic loss I square R represented by the P loss, then the power radiate P radiate is less than the input power P in. We know that when we give the input power, so we do not get exactly that amount of power. That means if we give 10 dB power as an input, so in the output we do not get the 10 dB exact amount power. There is some loss due to the ohmic loss. So we do not get the exact amount of the power. Then we can express the power radiate as a P radiate is equals to eta R into P in. and where the eta r is the radiation efficiency. So we can write the radiation efficiency as eta r is equals to P radiate upon P in. So radiation efficiency we can write in terms of the power radiate upon input power. So the ratio of the power radiate upon input power is known as the radiation efficiency. But total input power to the antenna can be written as P in as P in is equals to P radiate plus P loss. We know that the input power we can write as a P radiate plus P loss. P loss is nothing but the power is lost due to the loss. Hence, the radiation efficiency can be written as NR is equals to P radiate upon P radiate plus P loss. So we have just write instead of the P in is equals to P radiate plus P loss in this equation. So the power radiate and ohmic power loss can be expressed in terms of RMS current as P radiate is equals to I square RMS into R radiate, and P loss is equals to I square RMS into R loss. This is the radiation, R is indicate the resistance, or we can radiation resistance, and this is the loss resistance. Then the radiation efficiency is given by eta R is equals to R radiate upon R radiate plus R loss. So these are the relation between the radiation efficiency and power radiate and power loss, and this equation is the relation between the efficiency and radiation resistance and loss resistance. Now power gain, or we can say that the gain. The ratio of power radiate in particular direction to the actual power input to the antenna is known as the power gain of the antenna. So it is given as, or we can say the equation for the power gain is G theta phi is equals to PD theta phi upon P in. Here this PD is indicate the power density, and P in is, we know that this is the input power we have given to the antenna. So the relation between the gain and directivity. So now we define the relation between the gain and directivity. So the maximum power gain can be defined as GP maximum, or we can say this is the maximum gain is the maximum radiation intensity upon radiation intensity due to isotropic antenna. So we can write as the GP maximum is equals to U maximum. This is nothing but the radiation intensity maximum upon P in upon 4 pi. But the maximum radiation intensity is given by U max is equals to P radiate upon 4 pi GD maximum. So we can write this equation as eta R P in upon 4 pi GD maximum. And so by solving this equation, or we can write this equation, GD maximum is nothing but we know that this is the directivity or directive gain. So here instead of GD maximum, just we write the D. So eta R P in upon 4 pi into T. So this is the U maximum equation. Substituting the value of the U maximum in the expression of the maximum power gain. So here instead of the U maximum, we write this equation. So we get GP maximum is equals to eta R GD maximum, or we know that the GD maximum is nothing but the directive gain, or instead of the GD maximum we can write that the D. So this is the relation between the GP maximum, that is the gain and directivity. Now next one is the antenna beam width. Bandwidth and beamwidth is two different terms. Here we discuss about the antenna beam width. We know that the major beam, minor beam. So here that beamwidth we have discussed here. So this is the graphical representation of the antenna radiation pattern. So here, this is the maximum direction. We can see this is the major loop, and these are the side loops, and opposite of the major loop is nothing but the back loop. The antenna beam width is an angular width in degree. That means this is the angular width of the beam in degree is defined as the antenna beam width. It is depend on the radiation pattern of the major loop. So here, to understand this, we have plot this antenna radiation or the radiation pattern in this plan. So here the main loop we can see. So here two beam width is most important. First one is the half power beam width. It is defined as SPBW. The half power beam width is the angular separation in which the magnitude of the radiation pattern decrease by 50%, or we can say that the -3 dB from the peak to the peak of the main beam. So here the peak of the main beam is defined as the P. Here in the major loop you can see this is the P and -3 dB. So the angular distance between this point P1 and P2 is defined as the half power beam width. And the first null beam width is defined as this is the angular separation from which the magnitude of the radiation pattern decrease to 0, or we can say the negative infinite dB away from the main beam. So this is the first null beam width, or BWFN. We can also that beam width of the first null. We can see this is the null, the main beam width in the null direction. The distance between this, the null, two null, is known as the FNBW, first null beam width. So this is the two important beam width. First one is the half power beam width, and second one is the first null beam width. So here in this lecture we have discussed this topic. First one is the radian and steradian. Then we discuss about the beam solid angle. Then next one we discuss about the radiation intensity. Then we discuss about directivity. Then radiation efficiency. Then power gain. Relation between the gain and directivity. And last we discuss about the antenna beam width. So here in this lecture we have discussed this topic. Thank you. Hello and welcome to our channel Electronics and Communication Engineering. Congratulations to find us for learning. You are watching a lecture series on antenna and propagation that has approx 44 sessions and more are coming up. We have more than 1200 sessions in various lecture series on courses for electronics and communication engineering. Watch it and learn. If you like it, share it, subscribe it, and press bell icon to receive all updates on new session. Enjoy learning.